And could please join me in welcoming Gerard and Scott to give their presentation and demo. Demos rule.
G'day guys. So as was just mentioned, we're going to talk about simplifying OpenStack networks with routing on the host being in this case the compute node. Briefly we're going to talk about who we are, why when you're thinking about deploying OpenStack or have deployed OpenStack you should really care about the plumbing that's underneath. Then we'll talk about some of the options that you have to actually work with that underlay network as it's sometimes termed. And then we have a proposal, some things that have worked really well for us, and we've actually got a demo from that that is a nested OpenStack environment running on this laptop. So who are we? We are support engineers at Cumulus Networks, and basically we both spent time at other vendors in the networking other networking vendors before making the jump across to Cumulus about a year ago. What is Cumulus? And we'll do this with a bit of a history lesson. 15, 20 years ago, you would buy a Sun server and have to run Solaris. You would buy an IBM mainframe, you'd have to run AIX, or so they tell me. But when the components within those servers started to become more mainstream, the compute infrastructure really became unlocked. With x86, you started to get lots of different server vendors out there that didn't necessarily have a software offering, and it gave you the choice of operating system on the hardware you want. You could pick the best of breed. You had a whole kind of flexibility. But the problem there was that the networking proportion of it was still locked. You would buy a switch or a router, but you would have no choice in the way that you interacted with it and the choices that you really had there. And so what we're in now is a stage where we have something called open networking. As the server components became more mainstream, the networking components became mainstream as well. There's a couple of hardware vendors out there that supply the guts to most of the networking vendors that are out there. And with that in mind, why then, if everyone can do it, do you need to have a software offering? Why then can't you have a choice of operating system and a choice of hardware? Again, you can pick best of breed with a good supply chain, or you can go directly to someone who manufactures it. So Cumulus Linux is a Linux distribution, except that we run on switches. It effectively makes a switch look like a 32, 48, 52 port server, depending on obviously your port configuration. And we run on switches that are anywhere from 1 gig with power over Ethernet to 32 by 100 gig from a range of different vendors. Why does that make sense, and why are we really here and focused on OpenStack? Well, you've got 40 rack units of Linux in there already, in a rack, right? You've got those two on the top that are proprietary. In some way you need to hire someone else who has a very limited skill set or a specialized skill set to work on a very small part of your network. So the benefits that Linux brought is that we now have Linux through that entire stack. We have the automation capability that comes with managing large fleets of Linux. You can now manage large fleets of networking and Linux all in one consistent tool set. You now can sort of bridge the gap between your sysadmin teams and your networking teams as they start to have blended workflows. Again, you can treat your switch like a server. You do get the cost savings of having your choice of switch and your choice of operating system. We're not the only people out there that do this, so you have the ability to keep people honest and pick the best of breed that what suits you. But again, it all goes back to the disaggregated hardware of software. For us, we're really here because we want to think about Linux in the whole rack. We love Linux in the rack.
Oh, right. Okay. So it's interesting doing like a co-presentation with a peer, because you always have different opinions on things, and when you put some slides up, you want to kind of agree on what you put up. So basically, it's why should you care about the plumbing? And it's a question that me and Scott have kind of battled over for a while. So putting this slide together was kind of difficult. I'm sitting at my desk, and I call Scott over, and I'm playing this game. It's called the Plumber Game. Has anyone played it? No, some smirks. Basically, the aim of the game is you start up with a jumbled field. You've got a timer that's counting down, and you've got water that's about to go through some pipes. And you're going to kind of like move the pipes around and shift them around and connect them. So when I called Scott over, I could see his face kind of go, like, why are you doing this? You should be working on the presentation. But eventually he kind of goes, okay, this is a cool game. I'll play along. And the idea is there's many different tool sets that you have in this game. There's many different solutions that you can come up with. Essentially, it's about getting to a solution before time runs out. And the comparison to OpenStack networking is that there's many ways to do OpenStack networking. So what we want to do here is, talk through some of the tools in different ways and propose one type of solution. So the idea is not to prove the end solution or the most perfect solution, but show how we can take some of the innovation we put into Cumulus Linux, bring it down to the host, and provide one way of doing OpenStack networking. So you want to end up in the far right-hand side, not the game over slide. Yeah. Okay, so a couple of networks that you might be interested in with OpenStack networking. You've got your network, your tenant network, excuse me, and your provider network. So your provider network is kind of your connection into the real world, and then you have a bunch of options of how you can connect those things. So provider network, generally, you configure once or you configure a couple of times and you leave it be. And some of the more interesting network challenges come up when you've got tenant networks. You've got tenants spinning up, tenants spinning down, and then it pushes a bit of a requirement on your network. So how do I deal with that? So we'll go over some of the drivers, so some of the type drivers that you can use. The flat type driver, the easiest type of way to do this. So basically, you have a flat network, everything is just on the same thing. Your network doesn't do anything, it's completely dumb, but then it's really easy to configure. So a lot of the times you see this used in the provider network, so just a connection into an external router. But generally we want to keep tenants separated and keep tenant networks separate. So the next one is the obvious one we've been using for a while, is the VLAN driver. So VLAN is just put your tenants on two different subnets, separate them, and essentially that's how you separate your tenant networks. The thing with VLAN drivers is you've got to kind of make sure your network reacts when you react. So let's say I'm spinning up a new tenant with a new network. I've got to make sure that that VLAN is present. So you can either pre-provision or you can have some sort of hook in to configure the network as you go. The other one is VXLAN driver, or some other overlay, GRE, some sort of tunneling mechanism. Really say, hey, I'll provision some some underlay sort of network, basic connectivity, and what I'm going to do is I'm just going to tunnel between nodes. And what you get from tunneling between nodes is when you spin up something new, it just really doesn't care, it doesn't affect anything. So they're your kind of puzzle pieces that you've got to choose which one fits best. The other thing is you've got to look at your mechanism driver. So, there's a couple of options. The two I'm going to talk to is the Linux bridge and the OVS. So Linux bridge is kind of like a native Linux sort of bridge, uses the Linux kernel, basically what you normally expect from a server. And then you've got the OVS. So the OVS is a different mechanism driver that uses kind of a custom switching kernel, allows for different types of programmability. And then you've got the other mechanism drivers that allow you to hook into the network. And this is where it kind of started to get complicated. So you want mechanism drivers to say, when I do something, I want you to go out and talk to my network hardware, and I want you to reflect those changes. And that's when every vendor came up with a custom way of doing things. So they're your kind of choices within there. So what we're going to do next is we're going to talk about some of the designs and some of the approaches that people have taken, and then we're going to end on a demo of one approach that we want to show you.
Can I just get a show of hands who in the room feels like they're a networking person? Okay. Sysadmins, no networking, I hate it. Oh, that's quite low. That's quite good. And how many people here have done some kind of Linux networking, like put Quagga on a server or a home PC? Cool. All right, definitely the right audience then. So let's talk about the first design, and this is one that's sort of been tried and proved with OpenStack networks, and we're both support engineers, but being part of a startup, we get to do a bit of sales as well. This is a thing that always appears on an RFP. Can you do this? And this is a pure L2 design. And what we have is from the compute node, MLAG up to 2 top-of-rack switches or 2 leaves, and then from there another layer of MLAG up to a spine. Then depending on scale, you may go again. So this definitely works. This works without a doubt, but there are some drawbacks to it. One is that you have to rely on MLAG, especially when you're pre-provisioning all of your tenant networks, every one of those VLANs that you have a whole bunch of state that needs to be distributed between the two switches you connect to. You need to distribute port state and MAC state and things. So at scale, that becomes a little bit dangerous as well. The other thing is, if you lose one of your peers, you instantly lose half of your bandwidth. There were some things, and are some things that try to address this. One is to have a switch mechanism driver. And this is a driver that sits on the switch or talks to the switch to dynamically provision and remove VLANs as you dynamically provision and remove tenant networks. Again, there's some logic challenges to that. You need to have an understanding of the entire network from a switching sense. How to, which spine will I go through? Where do I need to provision these VLANs? It's a very, very heavy thing that again puts more load and more load onto the switches. But like I said, it definitely works. Then we start to get into some newer techniques. So we still have MLAG down in this design, but we have an IP routed fabric above. And in there, we actually map a VLAN to a VXLAN, which is an encapsulation technology which you can use with IP, and it uses IP routing as the fabric to which you get through and extend these broadcast domains. So in this, we have significantly shrunk the broadcast domains or have better control of it. We also get more scale. VXLAN is 16 million potential broadcast domains, where VLAN is 4,094. But again, we still have some complexities. This one tends to work quite well with an SDN type overlay, a Metacura, a Plum Grid, a Nuage, things like that. But again, we have this problem where we're provisioning tenant networks and we need to map the VLAN to the VXLAN. Again, you can have a switch mechanism driver. There's one that we have which does what's called hierarchical port binding, where we map a VLAN from the connection down to the leaf to a VXLAN in the routed fabric. This is in alpha stage with us. There is 1 or 2 customers using it in production, but again, it's somewhat of a complex maneuver. But we have taken some of the power of IP routing and put it into this network. The next option is layer 3 all the way down to the host, but only having a single connection. This works fantastically when you have distributed applications where you can use things like Anycast. In this scenario, we've gone from using the VLAN type driver in the last two to using the VLAN type driver for your host networking. Your VXLAN type driver for your networking. So with that, older generation NICs couldn't necessarily offload that to the NIC, especially with things like TCP segment offload. So if you're going to consider something like this, make sure your NICs are going to handle it, otherwise you may see performance problems. In the scenario, we're keeping that same IP routed fabric. We typically deploy with BGP, but OSPF is perfectly valid as well. We single attach every compute node to one switch. And what this allows us to do is advertise that compute node and have it be aware of the routed fabric. It's now one coherent ecosystem for a network and for all the plumbing that runs Linux. Like I said, it does rely on fault-tolerant applications or distributed applications, because if you ever lose the compute node or the top-of-rack switch, you have no redundancy from a networking perspective there. Which brings us to our fun design. And basically, we maintain that IP routed fabric again, where you have equal cost multipath, N-way by the spines, N-way by the leaves, but we also now take a routing stack and put it on the host OS. So with VXLAN, it's an IP encapsulation technology. You're only ever going to source from one address. So every compute node has one address, and you encapsulate up through there with your VXLAN for your tenant networks. In this scenario here, instead of having single attach, we can have multiple attach. And we can have N-way, rather than just with the MLAG scenario having only 2 possible uplinks, we can have 3-way, 4-way, 8-way, depending on your requirements. And if we ever lose a switch, we only lose n to the -1 of that bandwidth. So as we are a Linux operating system and we have a routing daemon called Quagga, we have taken, in this design, our Quagga package and installed it on these hosts so that we can then peer BGP all the way down and advertise our compute node out. And there's one thing that makes this a little bit more special. If anyone's ever provisioned routed networks before, you normally have a subnet of some kind. You'll have a network address, a broadcaster address, and a bunch of usable ones in the middle. Typically, point-to-points are a /30, so you have 2 usable addresses, one for each side. What we like to do in this scenario is something called BGP unnumbered. And what that is it allows you to have a single address, /32 or host address, and then using link local IPv6 communication, we can actually determine the next hop as IPv6, but share IPv4 prefixes. So what this means is we could directly connect 3.3.3.3 to 192.168.0.1, and they're both /32, and they'll come up and form a BGP neighbourship. We have no requirement to do subnetting anymore. So this means if you need another compute node, it's effectively plug and play into your top of rack. It comes up, it forms BGP. If you need more bandwidth from your leaf, you plug it in, it comes up, it forms BGP. And it's only ever a single IP address per switch. This gives you incredible flexibility from a networking perspective and a host perspective in terms of the plumbing into what you can scale to. Again, with BGP, you have, it is a complex protocol, but you can really take control and share what information is where and use it to help improve your security as well.
Okay, so we'll very quickly go over the decision tree and then get to the demo, which is the interesting bit. So basically, how do I decide what to use and what sort of design to use? Pretty much, what you want to know is what your communication method is. So you're going to use VLAN, you're going to use VXLAN, or you're going to use some sort of encapsulation method. If you're going the traditional VLAN, then you need your broadcast domains to be up on your network switch. So going to the VLAN route, it really pushes you to have some sort of layer 2 on your switches. So you either go have, layer 2 with VXLAN, VLAN into VXLAN with hierarchical port bindings with some sort of driver talking to your switches, you go out and pre-provision all your VLANs on the switch. If you go the other route, you can go through the VXLAN driver. You take the VXLAN driver, you make sure that the underlay network is up, that you have the routing fabric up and running, and basically any network that gets created from the tenant perspective gets tunneled between the nodes. So you go VXLAN tunnel, basically if you either have one or multiple routes. So if you've got one link to your switch, you can probably get away with not running a dynamic routing protocol. Once you get to ECMP type fabrics, many links to your switch, redundancy and all that sort of stuff, you probably want to go into what we're calling this future design. And what we want to show you is having the routing protocol, taking our version of Quagga, putting it on your servers, and then advertising it so that you've got a redundant fabric.
Cool. Hopefully the demo doesn't end up like this train. So we have a range of downloadable demos for Cumulus Linux with OpenStack available on our website. If I can exit show. Awesome. Cool. So let me just connect to the server 1. And so if we do, we're just going to go through the verify here. So what we've done is we've pre-provisioned a network here with a couple of tenants using the Linux bridge as the mechanism driver, VXLAN as the type driver, and we've got routing on the host, routing on the leaves, and routing on the spines. So this is the topology here. And that didn't render quite well. This is the topology that we've got here. We have a host. It has one IP address. It is running unnumbered BGP. It is 192.168.200.1. And then over the other side, we have a .2 as well. These guys are all running BGP. So if we look at a leaf switch, for example, those will come up in a second. Let's jump on here, F4 and quit. So the OpenStack config looks like this. Show config. We have quite simple Linux bridge drivers, the VLAN types that we're allowed, the VLAN types that we're using. We're using Linux bridge with L2 POP, and that just limits broadcast traffic and ARP resolution between network. We can talk about that later. And then we have a flat network as well, which is our provider network, which we saw going out to that external router. So on here, we have a routing daemon, which is running BGP. And you see here we have a whole bunch of tap devices. And here's our BGP config. So our upstream interface is now this particular interface on this Red Hat server. That's the remote AS, and we're doing the unnumbered, extended next hop. The other cool thing that we have on here is something called NetShow. This is something that one of our support brethren wrote. He was a bit sick of trying to find all this information in a Linux system that he could get in a traditional vendor. So in here, this kind of gives you a picture. We have our bridges per tenant, where it has the physical interface and the tap interface that binds everything together. We have further down, there are our physical interfaces and our tap interfaces themselves, our VXLAN interfaces. So these are the ones that actually connect the VNI out through our NIC. And these are the L2 logical sense there. So what we have on the switches is exactly the same thing. We have a whole bunch of interfaces that use the IPv6 link local information and exactly the same configuration. It's presenting you one common stack presented with one common tool. So in this case here, he's got a link upstream and downstream. Oh, this is the server, sorry. I think even I get confused. Let's keep that off the timing. So let's imagine now that we want to bring up another leaf switch. We've got server 2, it's got one uplink. We want to take that to 2 uplinks. So what we're going to do here is add uplink. And so what we've gone through, we've gone from a down interface to an up interface, and we've made the routing changes. So what we had before, again, it was this interface is peering BGP. We've only got one IP address. I need to have another IP address in there. For those of you who are familiar with BGP, it doesn't multipath by default. So we've also turned on multipath relax and maximum path 64. So if we had 64 uplinks, if we were ever so lucky, we'd have up to 64 paths for each route. Okay. So this is the new switch that we've brought up. Again, same config. And with any luck, we have gone from single attach to IP route show to equal cost next hops for that other server. Again, we have incredible flexibility and control using BGP to steer this traffic through our routed fabric. Again, if we added more and more, we could potentially have a smaller impact if we ever had a failure. We can dynamically take things out of a routed fabric because it's routing to minimise the impact to bandwidth down to your hosts. This is a very, very powerful tool. So, while this looks really cool in a nested demo on my laptop, this isn't really just a party trick. What we have done as a company with Red Hat is we have done this at crazy scale. So this was presented at OpenStack Summit in Austin last week. It is a 9-rack 300 plus compute node setup with Dell hardware, Red Hat's distribution of OpenStack, and our Cumulus Linux on the switches, as well as our Quagga package on the hosts, that was able to come up and be provisioned to the networking in 15 minutes, and the entire OpenStack deployment, including tenants, in 6 hours. So this is not just a science experiment. This is exactly the same technology that we just used at scale, at proof, in a huge OpenStack network. Thank you.
Good timing. Big round of applause for the demo. We do love a demo, don't we? And well done. Another big round of applause. It's always scary to do a demo. That's very cool. All right, let's get some questions. We can only do a couple of questions. I'm sure there's going to be a ton, so let's try to get a couple in really quick.
In your scenario there, are you injecting /32 routes into the fabric for the VMs themselves? Is that how it's working?
Not for the VMs themselves. They still do, traditional L2 networking going out to the network node. So we're simply providing the plumbing for that, and the only thing that's advertising at /32s are the compute nodes themselves for the IPs that are used for VXLAN.
So the fabric is then only used for the compute nodes to get to each other, so that they can establish those GRE tunnels or whatever.
Or VXLAN tunnels, and as well as back to the network node as well.
Okay, another quick question here.
So I'll cheat 2 really quick questions. So when you're having point-to-point BGP routes for every connection. What's the memory and CPU overhead for that? And what happens if your network goes down? Do you need to relearn every route?
It's really tiny. So basically the daemon has, it's not even recognizable amount of CPU and memory that it uses up. And BGP being the way it is, it's designed for things to go up and down, so convergence just relies normally on the protocol. So, I mean, the internet runs on it. We could talk depth later, but yeah, they're good questions.
And you guys have a booth here, yeah?
Yes.
So go meet them up in the Cumulus booth. Go ask them more questions. And another big round of applause. Thank you, Gerard and Scott. Fantastic stuff.